everyone, and welcome to our video presentation for problem-based learning tool in electronic instrumentation and measurement. We are group 23 from section 10. Let's start with the hardware setup. To conduct this experiment, we utilize an Arduino Uno board as our microcontroller and a breadboard, jumper wire, and a 10 kilo ohm network. For our light source, we use a 240 watt bulbs paired with a dimmer switch so we could smoothly adjust the brightness. To gather our true baseline light levels, we use a mobile lux meter app aligned direct with the LDR. To collect data, we wrote a simple script in the Arduino IDE. The code reads the analog voltage from pin A0, scale the raw 10 bits digital value spread into an actual voltage between 0 and 5 volts, and outputs it to the serial monitor every 1000 milliseconds for stability. Now let's look at our first set of empirical data shown here in data table 1. We record 10 distinct light intensities ranging from 111 lux up to 345 lux. For each step, we noted the output voltage directly from the Arduino serial monitor. To find the actual internal resistor of our LDR at each step, we use the standard voltage divider equation, which is R LDR is equal to 10,000 over V reference minus V output times V output. Look closely at the data. A higher clear physical pattern emerged. At a lower light level of 112 lux, the LDR maintains a high resistance of 992 ohms. However, as we increase the brightness using our dimmer up to 345 lux, the output voltage dropped to 0.45 volts, meaning the LDR resistance plummeted to just 9 ohms. This happened because incident photons provide energy to electrons in the semiconductor material, pushing them into the conduction band and lowering the overall resistance. When we plot LDR resistance against light intensity, we can see this downward trend visually. By applying linear regression to our data point, we obtain the data equation y equal to negative 31.5x plus 11546. The slope of this line represents the overall sensitivity of our sensor, which comes out to negative 31.5 ohms per lux. This tells us that for every single lux increase, the LDR drops its resistance by an average of 31.5 ohms. Alternatively, using a strict 2-point boundary calculation gives us a local sensitivity of, which is negative 22.41 ohms per lux. The final phase of our project involves automating of our data acquisition by linking our circuit with LabVIEW via serial communication. As you can see in our broad diagram, we configure a standard visual serial interface to stream data over our Arduino designed COM port at a matching 9600 bulbs rate. Inside a continuous loop, LabVIEW reads the incoming buffer string, converts it into a numerical value, and pipes it directly into a light waveform chart. Conclusion: this problem-based learning assignment was highly successful. We linked our Arduino hardware to the LabVIEW platform, successfully matched out the inverse relationship of our photoresistor, and accurately calculated its sensitivity matrix. Despite expected non-linear sensor behavior and environmental ambience noise, all course data acquisition objectives were fully achieved. Thank you so much.